Here we're going to talk about bond enthalpy and how we can actually use average bond enthalpies to approximate the enthalpy of a reaction. So bond enthalpy, it's the measure of the stability of a molecule. Essentially, we're trying to look at the enthalpy change that it would take to break a particular bond. And like before, we're going to have some nuances associated with how we define this. So it's actually 1 mole of the gaseous molecule breaking apart, not into ions or anything like that. So here we have H2 gas forming H gas plus H gas. Again, that's not a very useful chemical reaction, let's say, but it is the definition here of that particular bond. And you can see a few other examples here, and they all have some delta H's associated with them, some bond enthalpies associated with those reactions. And they're all positive. It takes energy to break a bond, remember. So these are positive values for delta H. So these can be used to measure the strength of covalent bonds in polyatomic ions as well, though it is more complicated. So some of these polyatomic ions, we then need to talk about the average bond enthalpy of a particular bond. Especially considering there were multiple resonance structures, as you might have recalled from some of these polyatomic ions. So we have to talk about the average bond enthalpy of a particular bond instead of total, for example. So some of this, that's why we are going to say this will be an approximation. It's not going to be an ever and always or an exact calculation. So like I said, we can approximate the enthalpy of a reaction by using the average bond enthalpies. So the delta H is the sum of the bond enthalpies of the reactants minus the sum of the bond enthalpies of the products. So that will be that is equal to the total energy input, essentially to break all of the bonds, minus the total energy released by that bond formation. So in doing this, you can kind of think of it like on the reactant side, we are breaking all of the bonds on the reactant side and then reforming all of the bonds on a product side. The difference in those bond enthalpies should be the delta H for the reaction. Here's a table of bond enthalpies. You have it on the back of your periodic table. I know this one's slightly different and it may have values that are slightly different than what yours say on the back of your periodic table. No big deal. Like I said, these are averages, so they are approximations. Different bonds will be slightly different in energy depending on their certain chemical environment. So these are approximations. So this is, again, kind of what this looks like, but pictorially, if you have enthalpy on the left-hand side, which is essentially just energy. Let's say we have H2 gas plus Cl2 gas forming 2 HCl. We can just break the bond between those 2 hydrogens and the 2 chlorines to get some intermediate stage, and then that will take a certain amount of energy to do that. And then we can deal with the reformation of those products, those 2 HCl bonds that we're referring to. If you ultimately gain more energy in the formation of those product molecules, your overall delta H will be negative. And that's why you see those product molecules lying lower in energy, in enthalpy, than the reactant molecules. On the other sort of reaction could occur where you have a positive delta H. The reactant molecules actually are more stable than those product molecules based on those delta H's and the bond enthalpies that you find in that table. So you can use this to calculate both negative delta H's or positive delta H's, exothermic or endothermic reactions. So here's an example problem. You can use the bond enthalpy table prior or the one on the back of your periodic table. I'll use the one on the back of the periodic table. But here we have methane burning in the presence of oxygen gas to form CO2 and water. So this is a combustion reaction, a fairly common one. So here, like we said, we can approximate that bond enthalpy of this reaction, where we're taking the bond enthalpies of the reactants minus the bond enthalpies of the products. Something important to note here is in order to know what bonds we're referring to, we're often going to need the Lewis dot structure. So if you remember oxygen, the best Lewis dot structure for O2 is actually O double bond O. Both of them had 6 valence electrons to start, so 16 electrons total. So this is actually the best Lewis dot structure for O2. You may have recalled also CO2 was C double bond O double bond O. Okay, so these were the best Lewis dot structures for these molecules. H2O, these were all single bonds, and for methane, CH4, we could draw the Lewis dot structure of that, which we should, and find that all of those are single bonds, single carbon to hydrogen bonds. Okay, so this is what this would look like. So the delta H, we would take however many carbon-hydrogen bonds we have in methane, and there are 4 single carbon-hydrogen bonds in methane. So we'd take 4 times the bond enthalpy of carbon-hydrogen. And then, like I had said, we have two O2 molecules here. So 2 times the bond enthalpy of oxygen-oxygen double bond. So it's important that we're looking up for that double bond. And these were our products. We have to include the stoichiometry here. So there are 2 O2s. So that's why we're doing that. Here there weren't 4 methanes, but there were 4 CH bonds in a single methane. Okay. Now here we have CO2. There is only 1 CO2, but every CO2 has 2 C double bond O bonds, right? There's one here and one here. So this is why it would be important to draw out these Lewis dot structures. And then lastly, oxygen, hydrogen, that's a single bond. Each water has 2 OH bonds. There are 2 waters, so there should be 4 total bonds that we're referring to here in terms of OH bonds. All right, so this is kind of the general setup. And now we're going to go to our table and look up an OH bond, a C double bond O, O double bond O, and a CH bond, and we'll be able to plug those in. So here you can see this is our table, the one on the back of your periodic table. It's a little different than the one before, but it has all these bonds in here. And here are all of the things that we need. Special note is CO2 is actually specially written in here just because it is common enough. C double bond O is often 736 as an average, but you see this asterisk, it's saying 799 in CO2. So that should be the value that we use here. And we can just grab these other values in kilojoules per mole and plug these into our equation. So again, here we have the equation. And we can plug in those values, like I said, that we just saw, taking the bond energy of these reactants minus all the bond energy of these products. And this is kind of the setup that you get. And you get a total delta H of negative 802 kilojoules per mole. This is an exothermic reaction, which we are familiar with in terms of combustion. We're familiar with that being exothermic, so this seems to make some sense. So this reaction releases 802 kilojoules of energy per mole of methane that you were to burn. So yeah, this is how we would go about estimating the enthalpy of a reaction using these average bond energies or average bond enthalpies.